Hello everybody, and welcome to example 3 on page 55 of the workbook. Here's another example of calculating cosets in a group. Another opportunity just to get used to this new definition that we're introducing in chapter 7. Okay, so let's read this example together. They'd like us to calculate the left cosets of the subgroup generated by 2 in the group U of 7. Okay, and then they ask us how many distinct cosets are there. All right, well, let's start by just writing out the elements in U7. This is a multiplicative group. Okay, and U7 is going to be the set of all positive integers less than 7 that are relatively prime to 7. Okay, and if you think about that, that's just going to be the integers 1 through 6. Okay, so there's our group. And our subgroup, the subgroup generated by 2, is just the set of all powers of 2. So if we wrote this out, it would look like the identity 2 squared, 2 cubed, missed one. 2 squared, 2 cubed. Okay, and so on. And because we're in a finite group, we would expect this list of powers to kind of wrap around and take us back to the identity. Okay, and let's do the calculation and just see that that happens. So we're going to get 1, 2, 2 squared is 4. And then what about 2 cubed? Well, 2 cubed is equal to 8, but if we take that mod 7, we're going to get 1, which wraps us around and takes us back to the identity. Okay, so this is just a 3-element subgroup that we're looking at, 1, 2, and 4. Okay, well, what about the cosets? Remember that we get cosets by just taking elements in our group one at a time and multiplying. Okay, we're going to left multiply by the subgroup. All right, and let's start with the nicest element in our group, the identity element. Okay, so if we take that and multiply it by this subgroup, we're literally just taking 1 and multiplying it through by these elements 1, 2, and 4, which is going to produce the same elements back again. Okay, so there's our first left coset. Okay, now before we proceed here, let's think a little bit about what we're seeing so far in this problem and what we've observed in previous examples. Okay, how many elements does our group have altogether? Okay, there were 6 elements in U7, and we just calculated a coset that already has 3 elements in it. Okay, so if we get the same behavior that we've gotten in previous examples, we would expect that there's probably only going to be 1 more coset, and that coset is going to contain the other 3 elements that we didn't get. Okay, the question is, which elements of U7 could we choose to produce that second coset? Okay, to help answer that question, I want to make an observation here that might really help when you're doing coset calculations. So notice that the coset that we already calculated has 3 elements in it. Okay, we use the element 1 over here to produce it. And what ends up happening is that if you chose 2 or 4 as your starting element, you would produce the same coset. And what I mean by that is that I claim that this set 1, 2, 4 would be the same as if you took 2 and multiplied through by the subgroup. Let's confirm that by direct calculation up here. Okay, what would you get if you did that? Well, that would be taking 2 and multiplying it by 1, 2, 4. Okay, and if you do that multiplication, you're going to get 2, and then 2 times 2 is 4. 2 times 4 is 8, but we're doing multiplication mod 7, so that's going to give us 1. Notice that that's equal, okay, to the set that to the subgroup. Okay, so this equal sign is true. We got exactly the same coset. And if we did the same thing with 4, I'll let you confirm that that would also generate the same coset. Okay, so the upshot of it is, if we want to get a different coset, we need to choose an element of G that's not contained in this set that we're looking at here. Okay, so not 1, 2, and 4, but something different. So how about 3? That's an element in U7 that's not in the first coset that we generated. Okay, and if you take 3 and multiply it through by the 3 elements that are in H, you're going to get 3, and then 3 times 2 is 6. And then 3 times 4 is 12, mod 7 is 5. Okay, and notice that we generated exactly the other 3 elements in U7 that were not in our first coset. Okay, and you could kind of confirm for yourself that 3, 6, 5, you would generate that same coset if you started with 6 or if you started with 5. Okay, same behavior that we saw up above in the first coset. All right, so let's draw a picture here. Okay, remember how in the previous examples our cosets partitioned our group, and the same is true here. Okay, in this case we got exactly 2 cosets. The first one looked like 1, 2, 4, and the second one looked like 3, 6, 5. There's our partition of U7. So how many distinct cosets are there? There are just 2 of them in this case. Okay, and that's the answer to the second part of the question here. Okay, and then the 2 distinct cosets specifically are just 1, 2, 4 and 3, 6, 5. All right, and that's example 3. So in the next video, we will talk about a lemma that kind of ties together a lot of the observations that we made in the first 3 examples here.